The properties of a substance such as sodium chloride or NaCl are determined in part by the type of bond that occurs between the sodium and the chloride ions. A chemical bond is a strong attractive force that is responsible for holding together two or more atoms. Sodium reacts with chloride to form a chemical bond. The substances involved in the reaction, sodium and chlorine, are actually quite different. Sodium chloride consists of a sodium cation, Na+, and a chlorine anion, Cl-. They're bonded together in a regular arrangement that we refer to as an ionic bond. An ionic bond is a chemical bond that is formed by the electrostatic attraction between a positive and a negative anion. The positive ion is, of course, the sodium cation. The negative anion is the chloride ion. In this lesson, we will investigate why this occurs and focus on sodium chloride since it's a prime example of an ionic bond, and as well it's a very simple system. Sodium itself is a pretty typical metal. It's soft, silvery, and it's also a good conductor. Sodium is also a highly reactive metal. So reactive, in fact, that when it's stored in its pure form, it's stored in oil. This prevents sodium metal from reacting with water in the atmosphere. If you take a piece of sodium metal and you were to melt it into a beaker, then fill the beaker with greenish yellow chlorine gas, a violent reaction takes place. The molten sodium glows with white light that gets brighter and brighter. As the chlorine gas reacts with the sodium, the greenish yellow colors begin to disappear, and a white crystalline solid is left in the bottom of the beaker, like this. Let's consider exactly what is taking place between the reaction that creates table salt, or sodium chloride, why it occurs. Understanding a simple reaction like sodium chloride can go a long way in terms of understanding the concepts involved with ionic bonding. Let's talk about the requirements involved to make an ionic bond. It's interesting. If you take a step back and think about it, the process of creating table salt, or sodium chloride, is actually pretty remarkable. You take two hazardous substances. Sodium is hazardous just due to its reactivity. It's so reactive it will react with the water that's in the air. And you take chlorine gas. Now, chlorine gas was first used as a weapon by the Germans in World War II. And here's a picture of some of the Allied soldiers walking through the gas fields in Europe. But the combination of these two hazardous substances, these two elements, yields something that is totally necessary for everyday life, but by themselves, the two substances are hazardous. Sodium is an alkali metal. The alkali metals are the most reactive group of metals on the periodic table. They are group 1A. Remember, the Roman numerals on the top of the periodic column in the A, or main group elements, give you the number of valence electrons that are found in the s and p orbitals in a particular element. This is just for the main group elements, remember. Since sodium is in group 1a, it therefore follows that it must have one valence electron, and a total of 11 electrons since its atomic number Z is equal to 11. Chlorine is a member of the halogen family. The halogen family is the most reactive group of nonmetals, and they are group 7a on the periodic table. It therefore follows that chlorine has 7 valence electrons and a total of 17 electrons since its atomic number Z is equal to 17. Let's draw an energy level diagram to represent the distribution of electrons in both the sodium and the chlorine atoms. So starting with sodium, sodium's atomic number Z is equal to 11. So beginning with the 1s orbital, sodium's 1s orbital is completely filled. The next highest orbital, the 2s orbital, is also completely filled for sodium. Next, the 2p orbital is also completely filled. Lastly, sodium's outer 3s orbital has only one electron in it, so he's lonely. Chlorine's atomic number is equal to 17. Just like sodium, chlorine's 1s orbital is filled. Chlorine's 2s orbital is also filled. Chlorine's 2p orbital is also filled. Chlorine's 3s orbital completely filled. Chlorine's 3p orbital, on the other hand, has 5 electrons. So it's got room for one more electron. And when ionic bonding occurs between sodium and chloride, sodium and chlorine, a transfer of the valence electron from sodium's 3s orbital to chlorine's 3p orbital occurs. So sodium is transferring this 3s electron to chlorine's outer 3p orbital. So when ionic bonding occurs between sodium and chlorine, a transfer of a valence electron occurs between the two atoms. Instead of drawing an energy level diagram, of course, you could always represent the valence electron transfer with the following equation. Sodium will use its abbreviated electron configuration, which is neon 3s1 plus chlorine, and chlorine's abbreviated electron configuration is bracket neon 3s2 3p5. And again, what's occurring is sodium is donating this 3s electron, and chlorine is accepting this electron into its outer 3p subshell. The result is the sodium atom loses its 3s electron, and the chlorine atom has accepted it into its 3p subshell. So when sodium loses an electron, its atomic number Z still stays the same. So sodium now has a positive charge associated with it, and its electron configuration, when it loses that electron in the 3s orbital, is that of neons. Now, chlorine's atomic number Z also stays the same, but when it gains an electron, it now has a negative charge associated with it, and its electron configuration is that of argons. So sodium loses its 3s electron. Its resulting electron configuration is that of neons, and it now has a positive charge associated with it. It combines with the chlorine ion, which now has a negative charge because it accepted sodium's 3s electron, and chlorine's resulting electron configuration is that of argons. So let's see if we can understand the chemical reaction that occurs between sodium and chlorine. Consider the noble gas family, group 8A on the periodic table. This group of elements is nearly unreactive. The reason that the noble gas family is completely unreactive is because their valence energy level is completely filled. In fact, a filled valence energy level is the driving force behind most chemical reactions, or all chemical reactions. When an element is able to achieve a valence electron configuration equal to a noble gas element, either at the end of the period or just prior to it, it has an overall stabilizing effect on the atom. Remember, sodium gave up its 3s electron. When sodium gave up its 3s electron, it gained an electron configuration equal to that of the noble gas element neon. Chlorine accepted sodium's 3s electron into its outer 3p subshell. When it did that, it gained an electron configuration equal to that of argon. So, noble gas elements do not tend to lose, gain, or share electrons because their outer subshells, their S and P subshells, are already completely filled with electrons. In other words, they have already achieved this stable electron configuration naturally. Noble gas elements naturally have an electron configuration with their outer S and P orbitals completely filled. So in general, the noble gas elements do not participate in chemical reactions. All other elements on the periodic table have to gain, lose, or share their valence electrons in order to fill their valence energy levels in order to become stable. In chemical reactions involving the main group elements, This process often involves the outermost s and p orbitals, since those are the last orbitals to be filled in the main group elements. Because of this, it's often referred to what we call the octet rule. And this is because elements gain, lose, or share electrons in order to reach what we call a full octet. In an octet configuration, there are 8 valence electrons. 2 in the s subshell, and 6 in the p subshell. So the general form that elements are attempting to gain is they want their outer valence electrons to be in the form, this is just for the main group elements, want them to be in the form ns2 and p6. And again, the reason it's called the octet rule is because if you add together the outer s and p electrons, it totals 8 valence electrons. Sodium has 1 valence electron in its outer 3s orbital. And by the octet rule, it will become stable if it has 8 valence electrons. So 2 possibilities exist for sodium to achieve an octet configuration for sodium's valence electrons. Sodium can either gain 7 electrons in order to fill its s and its p orbitals, and then its energy level 3 will be completely filled with 8 electrons, or it can lose 1 electron from its energy level 3 orbital, 3s orbital, so that its energy level 2 orbital will be completely filled. 2p2, 2p6. Now, generally speaking, the loss or gain of 2 or more electrons is not desirable. In fact, gaining or losing 3 electrons tends to be the limit. You can't gain or lose any more than 3 electrons. So, from an energy standpoint, it's far more favorable for sodium to lose the 1 electron in its outer 3s orbital, to lose it to get this outer valence shell electron configuration, than it is for it to gain 7 to fill its 3s and 3p orbitals. When sodium loses an electron, it has 10 electrons and 11 protons because its atomic number Z is equal to 11. Therefore, our sodium ion has a charge of +1. Remember that ions with positive charges are called cations. So we would call this a sodium cation. After sodium loses its 3s electron, we can now write the electron configuration for sodium's cation as follows. 1s2, 2s2, 2p6. So sodium's cation electron configuration is isoelectronic with neon. However, we wouldn't say that sodium has become a neon element because sodium's atomic number Z is still equal to 11, so it still has 11 protons. And remember that protons are the subatomic particles that define a given element, not the electrons. The neutral sodium atom and sodium's cation have a difference of 1 electron. Sodium's cation loses the 3s electron, so it has lost 1 electron. It has 10 electrons, whereas a neutral sodium atom has 11 electrons. So we can conclude that the effective nuclear charge for the electrons within sodium's orbitals is now stronger. When it loses 1 electron, it has 1 less electron to distribute this charge with. So we can conclude that the atomic radii for our sodium cation will be slightly smaller than that of a sodium atom because the effective nuclear charge has increased. Chlorine, on the other hand, has 7 valence electrons. It is in group 7A, so we know it has 7 valence electrons. In order to obtain a full octet, which is 8 electrons, its s and p orbitals will be completely filled. It can either lose 7 electrons or it can gain 1 electron. Now, since elements do not tend to gain or lose more than 3 electrons, gaining 1 electron in order to fill its energy level 3 is far more desirable. Once chlorine has gained 1 valence electron, it now has 18 electrons and 17 protons. So our chlorine ion is negatively charged. It has a charge of -1. The electron configuration for chlorine's anion is 1s2, 2s2, 2p6, 3s2, 3p6. So its outer p subshell is now completely filled. Now, this chloride anion is now isoelectronic to that of argon. But again, this isn't an argon atom because chlorine still has 17 protons, whereas argon has 18. The effective nuclear charge for our chloride anion is now spread out over 18 electrons instead of 17. So we would say that our chloride anion is slightly larger than a chlorine atom. And generally speaking, a cation's atomic radii is slightly smaller than its corresponding atom, and an anion's atomic radii is slightly larger. To conclude, we discussed one type of chemical bond. A chemical bond is simply the attractive force that is responsible for holding together 2 or more atoms. We discussed ionic bonds, which are a type of chemical bonds that are formed by the electrostatic attraction between positive and negatively charged ions. We described why this occurs, and we focused on sodium chloride, since sodium chloride is a great example of an ionic bond. We certainly have more to talk about in terms of ionic bonds, but starting with a simple system such as sodium chloride and using that as a generalization for larger systems will definitely help with the understanding of the concepts associated with ionic bonding.